comenzar el seminario de hoy. Muchas gracias a los que han asistido presencialmente, a los que tenemos en Blue Jeans y a los que tenemos en Facebook Live. Déjenme contarles algo acerca de nuestro presentador, el doctor Kyo Lee. Él obtuvo su doctorado en Ciencias Atmosféricas por la Universidad de Illinois y maestría en Ciencias de la Tierra y Medio Ambiente en la Universidad Nacional de Seúl, en Corea. Además, realizó un postdoc en el Instituto Tecnológico de California entre los años 2012 y 2015. Mientras realizaba su doctorado, se empezó a interesar en estadística y por ello ganó una amplia experiencia en la dinámica estratosférica, redes neuronales, química de la atmósfera y modelado de calidad del aire. A través de la adaptación y extensión de herramientas estadísticas previamente desarrolladas, el doctor Kyo Lee actualmente desarrolla métricas para la evaluación de modelos climáticos. Desde el 2015 es parte del Jet Propulsion Laboratory, el JPL, de la NASA, como investigador que se encuentra en Pasadena, California. Today we will have the honor to listen to you with the talk entitled Application of Topological Data Analysis to Multi-Resolution Matching and Anomaly Detection. So thank you very much, Dr. Kyo Lee. All you.
Gracias por la buena introducción. That's the only Spanish I could speak, so.
It's okay.
So, yeah. Oh, yeah, thank you, so much for the invitation. Especially Teresa, and it's just so great to meet so many people, in person and give a lecture, finally. So, right before the pandemic, in early, 2020, I was very fortunate to have a great opportunity to work with some mathematicians. Professor Yulia Gell she's a statistician, working at University of Texas at Dallas, and Dorcas was my intern student at that time. But during the pandemic, she now became an assistant professor at the mathematical department of Portland State University. And as the title says, today I'm going to talk about application of the topological analysis to earth science data. And this work is still in its infancy. But in this talk, and I really want to highlight that there's an enormous potential of applying topological data analysis to analyzing earth science data sets. And on the top of the slide, these animations show the temperature during the cold wave in February of 2021, and this one is the climatological temperature for the same period, and it shows how the temperature was the anomalous low for these 5 days. So let me briefly introduce about the topology and topological data analysis, TDA. So topology is the study of shape, and because all kinds of data we are dealing with, time series or temporal data or spatial temporal data, because data has shape, and the topological data analysis is some sort of the data analysis technique. And on the right of the slide, this is a typical workflow of applying the topological data analysis to the point cloud data. We apply in TDA we apply what we are calling the simplicial complexes to this any point cloud data, or this point cloud data could be the time series analysis. And once this simplicial complexes are applied, what it does is this TDA characterize the shape of the data. And how can TDA the way like the TDA characterized the data shape is like so it tried to get some like the topological summaries, and these like topological summaries are featured by like shape characteristics, and these shape characteristics include like connected components and like loops, and I will show that like some of these examples in the following slide. But it doesn't have to be limited to like a 1 or 2 dimensional. It can include all kinds of like high dimensional holes. And most importantly, TDA offers a nice summary of like a complicated like data. So I think some of you have already seen like this video. So, and the topologies like a copy cup and donuts are the same thing. And they are topologically like the same. If we can play this like a video, because all the parts like in this, like the liquid like containing like a part is actually like a connected like component, and this like a holder part is a hole. So these are like two like shape characteristics like summarizing the copy mark. And donut, we know that this is just a hole. So except this hole, like the rest of like a donut is like a connected component. So these are like topologically like the same. So any topologist like see them, they would say they are the same thing. Another good example. So I just pulled out this from like internet. So this is a map of the subway in Mexico City, and these are actually the same map, but I'm sure you have seen this map more frequently than this one. So this one, like this is actually shows the actual location of all subway like stations. But I mean, do people find like more useful information from here? What people care is like, so for example, if I'm here, like what will be the like the next station, and where are the like stations where I can transit to like another line or things. So in subway map, the key information we wanna know is like the connection and like their intersection. So these two maps are topologically like the same, and because like not everyone doesn't care about the exact location, but most of people care about like a connected like a relationship. That's why, this topologically summarized, topologically like same map is more useful. And so, and then what are the benefits of like the TDA? So these are somewhat abstract, but I will show some example like how we can leverage like these benefits. First of all, in like topological data analysis, shapes don't depend on coordinates. So these like the green like the ellipses are all topologically like the same. They are all one-dimensional whole. It doesn't matter whether it's like a perfect like a circle or just like an ellipse. Another thing, it also doesn't change like under smooth deformations. So in the previous slide, I mentioned that TDA like only try to characterize like some of those shape characteristics, like is it connected or like there are holes. So for our human eyes, these are all same characters, right? TDA, just that they are written in different like fonts. And it's very intuitive that like we all think like these are the same. But for example, if you ever wanna compare these, for example, these like characters with this other one, then you imagine like calculating bias and root mean square error, or even finding like a pattern correlation. For us, it's actually the same thing, but if you calculate like any matrix, even like pixel by pixel difference or a calculation, somehow it's gonna say they are here. But in topological sense, they are the same. And lastly, this is really important. It can provide, TDA provide compressed representation of shapes. So provides a nice. Before conducting like our research, we had done like extensive like literature. And TDA is getting really popular, like thanks to the booming like machine learning like application. But when we reviewed the like papers, we found only 2 previous like papers of a TDA application to earth science. The first one, like published in like 2019, actually shows that like how TDA can be applied to machine learning models using earth science like data sets. So in this paper, what they did is that they got images of like atmospheric like rainfalls, like making a landfall to the United States like the west coast. But also they found a lot of AR patterns that doesn't make a like a landfall. And they classified like those 2 and extract the shape characteristics of 2 AR groups. So one is making landfall, and the others don't make it. Then train like a support vector machine, and using the trained support vector machine, they just put on like some other like data that were not used for training, and made a model to make a prediction. Is AR going to make a landfall or not? And they found a great improvement in their like a support vector classifier model, by using TDA summary of these atmospheric river patterns, rather than using the original pattern data as it is. And the second paper, I mean this is also a very interesting application of like a TDA. And what the most surprising thing of this paper was when the paper was published in 2019, the first author's affiliation was a high school. So even a high school senior could apply like a TDA and publish like a paper. So that actually shows that the mathematical, the theoretical background of TDA is very complicated, but if you know the benefits and how to use those open source software or apply a TDA, everyone can use it. Even a high school student did it. And our paper we published last year is the third TDA paper in earth science, and these are of course our work is totally different from the other 2. And if time allows, at the end I will also briefly. So, in our work, we try to answer this question. Can we really use like a TDA to quantitatively compare 2-dimensional maps like these from different sources? And different sources, it means their resolutions might be different, both temporally and spatially. And for now, if the temporal resolution is different, there's really nothing you can do other than averaging data sets with the higher temporal resolution, match it to the data sets with the lower temporal resolution. But still, also when you are comparing this is some temperature maps over Africa, precipitation maps from Africa, different sources. When they have a different resolution, all the climate scientists, including me, what we have done is we have to match their resolution. And sometimes those rereading process is computationally expensive, and also whenever you have another data from different sources with different resolution, you have to remap all the data sets all over again. And you probably know that this Taylor diagram. This is still very useful, and quantitative, the summary showing the difference between different spatial pattern, and it's been used now for over 20 years since the Carl Taylor published its GRL paper in 2001. And interestingly, in our field, they're having lots of improvement in all kinds of analysis, techniques and modeling. And not so many people have tackled or like trying to find like some better alternative, than like a Taylor diagram. And Taylor diagram, I mean, I would say like, it's a like amazing, like, so like, I'm not really blaming, but sometimes like when we are like comparing like data sets or like even model evaluation, I would want to ask this question: does the exact location really matter? Well, for this one, like this is like a spaghetti plot of like a hurricane, like a track forecast model. In this case, the exact location really matters. So the answer for this question is yes. However, like on the right, so these are like the sea surface, like a height anomaly, like during like the 2 mega El Niños. Everyone remember there was one El Nino like in 1997 and called the Godzilla El Nino like in 2015. We all know that once you see like these like the anomalies like in tropical like Eastern Pacific, these are El Nino. Okay, and however, if we all know that this was like historically like a strong El Nino, and to say that there's another like a strong El Nino like similar to like 1997, that's the anomaly pattern to be has to be located exactly like the same location as, and the answer is absolutely no. Okay, then what about like the slight deformation? So for example, this is like the same like the spaghetti plot, and for example, and let's just assume that these were some real hurricane, like it made a landfall like to Florida. Then, if there were any hurricane forecast model which simulate the hurricane look like this at the exact location of a hurricane's eye, everyone said like this would be like a miracle. Because slight deformation, it's like just like a slight like a rotation of a hurricane. No one really cares. What really cares is about, in this case, even in hurricane track forecast, is like the location of landfall and the location of like the eye wall. Of course, like in this El Nino case, you don't really worry about deformation. Just wanna know that like El Nino is feature to be higher than like the normal like sea surface height anomaly somewhere like in the like. So that's why sometimes when you are using alternative like conventional matrix like a bias or like a root mean square deviation or Taylor diagram, those matrices are sometimes very sensitive to slight deformation. So if you have like El Nino and just a slightly like shift to like the El Nino, calculate the RMS3 or the pattern correlation. Sometimes
can you stand closer to the screen? Because the people that are hearing from Facebook and other places, close to the screen.
Oh, here? Oh, okay. Oh, sorry. So that's the like one issue like of the conventional like the matrix. And so qualitatively we can all say they show like a good agreement. They look similar to like each other. But we are all scientists and we want something like a quantitative like a matrix to saying that like these two like have some similar spatial patterns in a quantitative way. And there are a group of people like who try to propose like some different ways to compare spatial patterns different from Taylor diagram. And the special forecast verification method, the interconfiguration project, is from the National Center for Atmospheric Research. And what they propose is all 4 different methods to compare patterns And these methods are like not as sensitive like to the slight deformation or like a slight shift of like the patterns as Taylor diagram. However, there are still like issues. Even like to apply all of these four methods, they still have to match the resolution. So so this project like figured out some ways like to avoid the oversensitivity of conventional pixel by pixel comparison, but still they could not skip the regridding process. So the objective of our work was like we wanted to build a robust and reliable methodology that compared the spatial patterns from different sources without regridding them. And I will show how it works and so. And our use case, we analyzed the temperature. One is from the reanalysis data, so it is almost the same as a ground observation. And the other is a climatological temperature from NASA's atmospheric infrared sounder on the Aqua satellite. So our analysis period was the first one was during the February of 2021, and the second one was the summer in 2021. And this period there was a massive a cold break in southern parts of the United States, and this one there was an extreme heat wave in the northwestern United States. And as you see here, so these data sets have a different spatial resolution. So the MERA2 reanalysis has a slightly higher resolution than errors. And of course, when we apply the topological data analysis-based matrix, we compared it with all conventional matrices as well. So our use case, we chose the mid-February in 2021. And for those who live in Texas, United States, this week of February, mid-February was a complete a nightmare. So these two plots shows the nighttime light map over Houston, Texas. So this is before the cold wave, and this is right after the cold wave. And now you see that how many people got suffered from the blackout after the cold wave. And it was, meteorologically, it was very interesting because there's always a cold pocket of air we call the Alberta Clipper. This is originating from the northern part of Canada, and sometimes it comes down to the northern part of United States. But in 2021, this cold pocket of air came down all the way down to Texas. So, and this is the analysis domain for the February 2021 cold wave case. On the top, this is from the reanalysis data for the Great Plains area, and the bottom is what we can expect, the temperature we can expect, because these are climatology data from satellite observation. And and you see that this is temperature colder, and whenever we are showing this kind of map, people actually want to see, if your students brought this kind of map, you would ask the student, make us some difference plot, temperature difference plot. So in this case, I cannot calculate the difference by subtracting this reanalysis from errors because their resolutions are different. The MERA2 has higher resolution. So what I have to do is I remap the data into the same grid points as errors, and I can finally calculate the difference. And and this shows how severe the cold wave is. The unit is Kelvin. So in some parts of Texas, it was 30 degrees colder than climatological temperature. So Now that this slide describes the application of a cubical complex. So this is one of the simplicial complex that we can apply for the topological data analysis. So any temperature map look like this can be viewed as these square pixels with some values. And what this cubical complex does is, so it searches the lowest value, in this case 240 degrees, and the highest value within the domain. In this case, that's 255 degrees. Then there is a threshold value called the omega here. And what it does is that the cubical complex algorithm increases this omega from the minimum value toward the maximum value. And as the threshold increases, here I create out all the pixels whose threshold, whose values, temperature values are lower or equal to the threshold. So in this case, these are all grayed out, and you see there's more pixels are grayed out. And at some point, when the threshold reaches the maximum value, all the points will be gridded out. Then what TDA, the algorithm does is so now it characterizes the shape of these gray boxes. So for example, before I apply any filtering algorithm, everything is just white. So there's only one connected component. Because every pixels are connected, have the same color in this case. But here, now you see that there are two connected components. And at this threshold, it became one. And now in this threshold, you have you still have a one connected component, and there's a hole. And what happens if we keep increasing now? There are two holes. So we see that as we change the threshold value, there are some patterns created, and there are some patterns disappear. And all of these, the life and death of topological, shape characteristics, are summarized in this diagram we call persistence diagram. So these, red dots actually shows the birth is the x-axis, the death is y-axis. When connected components were born and when they died, and these triangles show when those holes were born and when they died. So these values of 16 temperature, their shape characteristics are summarized as the two dots and two triangles, the persistence diagram. And at the earlier slide, I mentioned that we just apply a simple linear complex to any point cloud data, and that's everything it does. And we don't really have to choose the cubical complex. Cubical complex is a very fast algorithm, works with gridded data, those reanalysis or data from the client model. But there are ways to apply some other filtration. So this lower square filtration, it works really well if it doesn't have the data in all grid points. So, for example, for a data set from the ground-based stations, they are not really regularly spaced. In that case, you can also apply the lower square filtration. And if we apply lower square filtration to this pixel, we can get exactly the same persistence. And also there are other the filtration algorithm, and this is actually more popularly used a simple linear complex. So the Beatrice this Fourier complex, just it mostly cares about the distance between these dots, and as I showed, like in the cubical complex example, the spatial patterns of this point cloud is summarized on the persistent diagram, or you can also generate the barcode. This barcode is exactly like the same as the persistent diagram. It just shows like when the pattern was like born and like when it died, and but doesn't really use the y-axis. It just shows the like the lifespan of its shape characteristics as a barcode. So this map, this temperature map on February 15 of 2021. Okay, I can apply when I apply the cubical complexes now, as I showed in the previous slide, it's gonna create out all the values as we change the threshold. Then this map is just summarized. The spatial pattern of temperature from this map is summarized on this persistence diagram. And I think someone's gonna question so once we have a persistent diagram, can we actually retrieve this temperature map? Yes. It's the one-to-one conversion. So as long as we keep all the information, we can revert this persistent diagram and generate the temperature. So what happens? So if we apply TDA to these both maps, so the top one is the Merac-2 reanalysis, the actual observe the temperature, and this one is like a climatological map. So we do the same thing. So we are summarizing their spatial patterns from persistent diagram. Then once we have these two persistent diagrams, as I told you, you might want to remember that their spatial resolutions are different, but once they are on the spatial persistent diagram, we can calculate the difference between two persistence diagrams. And what we wanted to argue was that the difference measured between persistent diagram can represent the difference in spatial patterns in original temperature map data. So, and we also calculated the conventional matrix, a root mean square, a deviation. But so these are all daily climatology for February, and these are Merac-2 data for the 28 days in February 2021. But everyone knows that I cannot just calculate the RMSD between Merac-2 and Air's daily climatology. The first step I have to do is I have to regrid every daily map into the Air script. Then I can calculate the root mean square and we calculate this to compare with TDA-based matrix. But TDA one, so we just convert every single map into this persistent diagram. Then once we have a persistent diagram for each day, one from from those from the Merac-2 and the other maps from the Earth's climatology, we can calculate the spatial time distance and measure the difference. And in the following slide, I'm gonna compare how these partial time distance looks like compared to the root mean square deviation. So now this is the daily temperature, from the February 1st through the end of February in 2021, and this daily temperature is averaged in Texas. So the y-axis is temperature, and this red line is the partial time distance we calculate between the persistent diagram from Merac-2 and Earth, and this green line shows the root mean square difference. And both matrices have the highest value on February the 15th, indicating the difference from the temperature difference from the climatology was the largest on that day. At least, yeah, that part is like consistent. But you see that like they're not really like they don't really have like a good correlation. So I just made a scatter plot showing that like so the x-axis is like a root mean square deviation, and the y-axis is Wasserstein like a distance. So the TDA based like a matrix. They're kind of like a consistent, but don't really show like it. And also interesting thing is like the root mean square, like this green curve, it's very symmetric, almost symmetric with respect to like the February like the 15th. So it's just a symmetric curve, but in this Wasserstein based matrix, whether you are using regraded data or the original data, they show like a huge difference like between the like a cold wave and after the cold wave. Here, like I define the cold wave as the day with the lowest temperature in Texas. So then what happened? Why sometimes like they look like a consistent, but sometimes like they are totally different? And I found the answer actually by plotting temperature averaged like only northern part of the Great Plains. So the blue line is the same from the same as the previous slide, but this black line is an average temperature in the northern part of my domain. So without Texas, only like the average over North and South Dakota, Minnesota, and Iowa. And not surprising, this is not surprising, I mean, the cold wave, I mean, for people living in Texas, February 15 was the coldest day, and that's the day, like a lot of people, millions of people, like suffer from like a massive blackout. But for people living in northern part of the Great Plains, the cold wave started like earlier. Not surprising because the air, cold air is originating like northern Canada, and it also lasted longer. So here's some problems. So depending on where you live and like how to set up like your domain to average like temperature, you can have a different definition for cold wave. And another thing, like another issue of like using like the temperature data to define like the cold wave is when did this cold wave start and when did it end? And this temperature curve is like kind of really smooth, and it requires like some different temperature threshold values if you want to define cold wave. And now like these two, they are related to like a certain like the synaptic meteorological pattern, the same pattern, but it's hard to define cold wave. Because beginning, onset, and demise of cold wave using temperature data only. And this is so I made a scatter plot between these blue curve and like the black curve. So the x-axis is the temperature in Texas, and y-axis is the temperature in northern part of like a Great Plains. And these numbers are like the days in like February. So there are a number from like 1 through like 28. What I actually did is, so even using like this temperature curve, I did a very quick and dirty clustering analysis. So for somehow I could group these 4 days, like from like 11th through like 14th, as a one group, and those like 5 days, like from like 16th to the 20th, as the other group. And see this, look at these like red curve. It does look like these two groups are different in TDA sense. But I told you the RMSD curve looks almost symmetrical with respect to the February. It doesn't show any difference. And these are actually masked, like so. These 2 days are like before the coldest day in Texas, and now these 2 are like the after the coldest day in Texas. And if you just look at compare these two, their spatial patterns are different. probably like the most distinct like feature is like a cold pocket, the bullseye like in Colorado, which is totally different from climatological. Which you can find like some of the like we call it like the bullseye like in climatological pattern because of like their like high altitude like in this area. But these like the patterns are definitely different from this, and somehow because the RMSD is some average like a difference matrix like for the entire like the domain, the RMSD based methods or like the temperature, like especially average like temperature, didn't really reflect the difference in these like a special pattern. But the TDA based metric somehow captured that and saying that like these like a special pattern after like the February 15th is like more deviated from the temperature climatology map. And we also wanted to show that like during the cold wave, like the people know that like on average, like during the cold wave, it's definitely like colder compared to like the average temperature. But there could be also another important factor, like the day-to-day variability of like the temperature. People probably like wanna know like how long like the cold wave or like some heat wave, like those the anomaly patterns like existed, and like what are the like variability. And we also like to look at the to measure the day-to-day like the variability. We also calculated the Barshstein distance within like these like same group. So we calculate the Barshstein distance between these 5 different days. Well, actually not just 5 different days. We have done the calculation for the entire February and see like how the Barshstein distance measures the day-to-day variability in temperature pattern. And these are the results. So, and you can also calculate the root mean square distribution. So these are like all the root mean square RMSD distributions when you are randomly picked like 2 out of like 5 maps. And now like these like green dots show the distribution when you are using regraded data. So the regraded data, it has like a lower resolution than the original data. But can you actually see any difference? I mean, it shouldn't show the difference because my regrading, like the regrading I applied, it has to keep the overall mean and overall like the variance. So it doesn't change. So the day-to-day variability should not really change. So that's why the distribution like not find any difference between 2 distributions. However, if you see like this Barshstein distance like the distribution, you see that there is a more variability in the original data than the variability within the regraded. And I think this is a very intuitive and like a more meaningful thing. Think about it, you have a high resolution map and using like a conventional matrix, like a root mean square deviation. Once you like upscale the high resolution map into like a low resolution map, there's no way to say that you are also smoothing out some day-to-day variability by generating low resolution version of your data. However, it actually shows, again, it's also gonna decrease the day-to-day variability as well, because the special patterns of the difference between smoothed pattern, it shows like more similarity compared to like the original data counterpart. And this is like not surprising because you have like a less number of like pixels and the pattern is like more smooth. So this one, like the important thing is like also we can calculate the original data and the regraded data. And this is all because the regraded data has more smooth patterns and losing all the higher resolution feature. And if that's it, yeah, we are losing some information from if you are upscaling high resolution data, low resolution. And another thing you can do with this persistent diagram is you can apply all different kinds of clustering algorithms. So here, you don't really apply the clustering algorithm to the original temperature. And the original temperature map, even if the domain is confined only for the Great Plains area in the United States, it still has thousands of points. Compared to that, these persistent diagrams don't have as many points as the original map data. And if you apply any clustering algorithm, you can clearly distinguish the period where you can really call the cold wave occurred. And it clearly separates the zeroth dimensional shape characteristics and the first dimensional the loop characteristics. So both components can be used to detect the cold wave even without knowing how the temperature that look like. And let me move to the another use case that's something I found that they even named this heat wave event. They called it the 2021 Western North America heat wave, and there was the omega shaped blocking at 500 hectopascal level, and it trapped extremely hot weather. These numbers are all Fahrenheit, so this area usually people live people don't even need air conditioning in summer, but temperature went up to even 45 degrees in this area. So this is kind of similar to the Texas use case. So now this is the blue curve is the daily mean temperature, and we have the same issue. How can you really define? This is the onset of the heat wave, and this is the demise of the heat wave. It's really hard, and it's also very symmetric, with respect to the highest the day, and the RMSD, this the green curve, it's almost shaped exactly the same as the temperature map, which is this temperature curve, which is this is the special average. And this is also some sort of a specially average matrix. So it's not surprising. And the information from these two curves is kind of a redundant. But if you see the Bartenstein distance that we calculate for every day, you see that there's a sudden increase and also there's a sudden decrease. Following slide, I'm going to show what happened. Again, it's a smooth curve. At the top is the specially average temperature, and this is the Bartenstein distance. So the Bartenstein distance. Now, if anyone sees this curve, they want to define this might be the beginning of the heat wave, and this might be the beginning of the end of the heat wave. And what we found is, most of the Bartenstein distance is contributed from these bullseye patterns in the eastern part of Washington state, and this was developing, but somehow while it got weakened, now the Bartenstein distance says this is getting more similar to the climatological temperature. So the summary. This, I told you, we are still working on that. Friend and my colleagues and I downloaded all the data sets for temperature and humidity data sets over South Asia, over India, Pakistan and Afghanistan for last month. And so we're still like working on that. We are writing like papers on that. But the most important thing I want to highlight is like so our like the original like the goal was like to define like some quantitative matrix to measure similarity or like some difference in spatial patterns, which have like a different spatial resolution. This was our like original like goal. But we found out like this Weierstrass distance, which is the topological data analysis-based metric, it enables like this advanced anomaly detection, which cannot be done using other conventional matrix. Like and the conventional matrix here means they are mostly include like some sort of like the average over space. And that's all because like the TDA captures like some of the higher order variability. This is not well captured when you are averaging data. So, and the potential application, I'm just listing a lot of applications. So TDA, as I mentioned in the earlier slide, it can be definitely applicable to 3 dimensions. And so even we can look at the topological features of a hurricane or like convective storms or like tornadoes. And also the TDA has been used in other fields to reduce noise. You can, on the like a persistent diagram, like a space, you can define that some of the like a pattern which doesn't like live longer than certain threshold, you can define it as a noise and bring it back to the like the original map without those noisy patterns. So that has been like an application in other fields, not in earth science like yet. And the last like the last thing like that I want to highlight is it's been very popular to apply the topological summaries in machine learning. So to convince like some funding agencies and like those who are funding like the JPL and like the NASA's program, I have like submitted like so many like proposals, and like I'm just listing like some of the like the successful like proposal, but to win like some of these like small fundings have to write like so many proposals and like and mostly these are like from like the JPL's like internal like support like, but finally last month like we won some like a big funding like to continue like our like TDA based like study, and this is like the comments from the NASA review panel. What we proposed is like we are developing geometric deep learning model like for detecting the anomalous events, and the key technology we are proposing here is using that topological summaries. So our like deep learning model is gonna use like a TDA summary, not the like the original images, and we got like this kind of comment. I didn't know that like someone can use like the word like fascinating when they are reviewing like papers or proposal. So finally, we are making some progress, and also, I mean, it would be nice. I mean, if any of you are interested in like in working with me and like my colleagues and like learn more about like the TDA application. As I showed, I mean, like our paper published in 2021 is the third TDA paper in earth science, and the one I presented today, if we publish, I'm sure it's gonna be the fourth TDA paper in earth science. And this is, I mean, we believe that this is gonna work. So this is about the paper we published in 2021, because we had a mini project like in 2020, applying like the TDA to the earth science like data, and develop like a neural network model using this TDA summary as an input. So if your deep learning model is the artificial neural network model with at least 3 or like more like hidden layers. If those deep learning models are using topological summaries as an input, not the original, like the spatial temporal data. We can call it geometric deep learning models, and we could forecast like the COVID-19 progression and clinical like the severity by using deep learning models. So I'm leaving a copy of these slides like on this computer, and like we'll send it to like Teresa. So if you're interested, ask her to like copy, and also if you have any questions, just send me email. Thank you.
I was wondering what I missed by computer first. And I also was wondering what is the computational cost of it. Because on one hand, we save time interpolating, what we are doing most of the time. And on the other hand, we have to do this, so I don't know.
That's a
Very
great.
expensive or not?
Oh yeah, that's a great question. So the summary of slides. So yeah, then we don't have to regrade when you compare data. And also the main reason that I chose the cubical complex, like over like some other super easier like complexes, is the computational cost. It's computationally like really cheap. So you can even use your like laptop.
Cool.
So it doesn't burden your like a computer system.
Even for high resolution models.
Yeah, it's very simple.
That's
And
great.
if you need any working example, just send me an email, because
Yeah,
now I'm working with some other like students like to apply this TDA to the cis-surface height data. And our like working hypothesis is the ocean models with a higher spatial resolution can better represent all the details in SH like the patterns when you compare it to the like satellite data. And all the traditional metrics, I mean now like the satellite data set has very high resolution. But when you compare like high resolution data sets to like a satellite data set, that's kind of okay. But when you have models with a low resolution, you have to match like even the high resolution observation into the low resolution model, because we really don't want to artificially generate the high resolution like this. So so some of the people like I'm working with from the Ujjo Institute, like they really had a hard time to quantitatively like argue that these high resolution data better represents like some feature compared to the low resolution simulation from the same model. And they are now applying like these, and here getting happy, and also had a lot of issues. Yeah, of course, because those offline TDA to ocean data, it's also really tricky, because somehow like when you apply the same like the cubical complex, that persistent diagram reflects not only the data structure but also all the coastline, because those are all missing data. So now we try to figure it out like how to really what kind of like the complexes might work like the best when you have like those data from
Primero voy a abrir preguntas para los presentes, después vendrá Blue Jeans, donde podrán abrir micrófono, y finalmente preguntas del chat de Facebook. Que si alguien tiene una pregunta, alto como mariachi, porque no tenemos aquí. Sí.
I don't know if you have talked to some of the old synoptic methodologies that used to make weather maps analysis. No, I mean, I'm saying maybe like Richard Pash or Ludwig Shelton, who was at JPL 4 years ago, and still at Oregon State. maybe it's a good guy to talk to, because at that time they could look at a movie or a series of plots, and they would come out with very good analysis. Topology analysis in methodology is not new. It's very old. What is very new is the massive use of computer resources. See? But many of the things not many, some of the very basic things that you talk, I heard of them about 40 years ago. So I think it will be interesting to talk to some of these old guys in the National Weather Service or Ludwig Shelton is a good person. I remember him looking at a movie before a presentation, so that a movie of the world, and then telling us what he was understanding from that movie. Okay, so just my comment.
Yeah. So I would say it's still using topology the earth science data and getting some quantitative summary or measuring the difference is still in very in the early stage.
Yeah, and one thing to keep in mind, even though to a topologist a cup of coffee and a donut is the same, you cannot drink a donut.
Yes.
So, they're not the same.
Yeah. So we wouldn't really argue that the hurricane in Atlantic Ocean or Gulf of Mexico is just even though it can be topologically similar to the typhoon in Asia, because the location really doesn't matter. We wouldn't really compare those apples and oranges, but something those El Nino patterns. Like you mentioned, we see those maps and everyone knows that this is El Nino pattern. But how can we really define the quantitative measures? And you probably know that the Nino-3 indices, when you calculate those boxes, there are some El Ninos which doesn't have a really strong signal. One of those boxes that are used to calculate the Nino-3 or 4 indices. And so people define some other the indices and call it Moki El Nino. So if you are using some sort of the topological definition of El Nino. El Nino is some special pattern over the anomalously high sea surface temperature or sea surface height in somewhere tropical the Pacific. You don't have to worry about where to put those boxes to calculate the eastern and western tropical Pacific temperature SHD.
Thank you. Any other question? De la sala. Blue Jeans, entonces la gente de Blue Jeans, si quiere, puede abrir el micrófono, si hay alguna pregunta.
I think there are some chattings.
I don't have to. Están preguntando algo por el chat, porque están como 6 personas, hay como 6 comentarios. Ok, ya no. Aquí, Julio, ¿quieres preguntar algo?
Yes, thanks very much for your talk, very interesting. Can you explain a little bit the connection that you mentioned with optimal transport in some of the slides that you...
Oh, he's asking the slides. Sorry.
Yeah, you have to move the slides.
Oh. Okay.
Which one is
Well, the connection with optimal transport. Can you hear me? Maybe you cannot hear me.
Sí, te oigo, sí te oímos. Es que no podemos cambiar el... Ahí está.
Okay, no, in some of the metrics, you said that it was connected with optimal transport.
Optimal transport.
I don't remember which one. You had it in parentheses. You said it's like that one.
Here, that one, the last. Go back.
Next.
That's one.
Yeah.
What's the connection between the Wasserstein distance and the optimal transport? Can you explain a little bit that?
So the Wasserstein distance is a matrix originally designed to quantify difference between any two probability density functions. So in this application, we view that in like this. Look, you see like some density and oh yeah, this is some sort of like density function like along the one-to-one line. So and that's how like we applied this Wasserstein distance as a metric, and pretty much also all open source like TDA packages like Untitled and R, they are including like a Wasserstein distance as a metric to measure difference between persistent diagram. And our case there, we use like the second order, so the observation that R like equals like 2, and I asked the statistician colleagues and like why are we using like 2, and couldn't really understand like all the formulas like they sent, and they kind of told me like they tried all other numbers and like but somehow like in your case like the second order Wasserstein works the best.
Okay. And second question is what kind of are there any methods for vectorial or vectorial fields? And can you comment on that?
Oh yeah, so the VR complex I showed that because we used the So we used that VR complex like in the COVID-19 model, because the COVID-19 model like the hospitalization and all the progression data, we use this from each county of the 3 states, California, Texas, and Pennsylvania. They are not nicely gridded as this temperature map. So they are kind of irregularly like spaced data. And so even though this is more like a computationally like expensive, like this is like relevant when the data has some graph like a structure, not in a gridded format. So yeah, and somehow like this VR complexes are like more popularly and like widely used like in topology like application, because not all other fields like have nicely like gridded data as we have. So this is also related to the computational like.
Okay, thank you very much.
Gracias, Julio. ¿Alguien más de Bridges?
Oh, I had a question. So, okay, so here you're comparing sort of the difference between two models for essentially the same events, but traditionally in persistence homology, you compare some qualitative phenomena that should be different, and you're using the same model but with different data sets, right? And then that's where you use the Wasserstein distance.
Yeah, so one is the actual observation of 2021, and the other is the long-term past observation, and it's an average of like a long-term observation. So none of them are from model. I mean, we use those reanalysis data as observation. So one is the observation. So this is, we can say that this is observation, and this is also not from model. So this is the temporal average of the data for 17 years, not including 2021.
Okay. And so my the other question I had was well, coming back to efficiency, because in a sense, you were saying that comparing distances using the Wasserstein distance, it's easier because you have less data points than say in your color maps. But on the other hand, to compare these persistence diagrams, you need the color maps. So why is it more efficient? I mean, you have to.
Oh, because it has the smaller number of points, first of all. So for example, here like 16 temperature values are summarized like as 4. And so you can kind of like scale down like the number of like pixels. And also when you apply like the clustering, like you can apply the clustering to the original temperature maps and also to the persistent diagram. The efficiency is like much, faster and like greater like when you are using persistent diagram. And using like that summarized like the topological information and applying it to like a machine learning. So like that's also key for the geometric like machine learning models, and it also I think people use it like to improve like the efficiency.
Okay, and one final question. So here it worked out well that you know that you have a two-dimensional map, and sort of persistence diagrams are usually only for the first homology, right? But if you want higher homology or you have higher data sets, have you used anything like that? I mean, for where higher homology is important?
So yeah, so I actually left one slide at the end because yes, so the higher dimensional, we haven't really applied it to three-dimensional like a data set yet, but we are now like expanding this the TDA algorithm like to the spatial temporal like a domain, because as you mentioned, as I did, you can apply like a TDA like to each daily map, and you have as many number of the persistent diagram like as the dates, like the same as the number of the dates, and like if you have a 30 dates, you have a 30 persistent diagram. But you can still apply, and but that's not probably the best way for like the anomaly detection. What you wanna do is like you apply like the entire like spatial temporal like data, and wanna get some persistent diagram like summarizing the entire like period and like how those like daily maps like change like over time. And yeah, and this is this applying this like a zigzag like a persistence, which is using spatial temporal like data and find and detect the anomaly, is the key part of our like the proposal, and that the new project will start very soon. And we haven't really applied, and I would say like nobody has applied it to earth science like data yet, but our colleague like applied to some observation, graph observation, and also some the data from like Mars, and found out this is also another efficient tool for the anomaly detection. So if there's some anomalous observation like over time, it can detect and saying that there's something like the going on, like something different things are detected in persistence diagram space.
Okay, thank you.
Gracias, Daniel. ¿Alguien más de Bridges? ¿O de aquí también? Parece que...
Thank you very much for you. But I have a question different from you. I understand that GPS is going to put all open data at the cloud. Is that true? And what is going to mean for the users?
Oh, so this is a different story. Like so, for us, cloud is what's making weather and like blocking sunlight and like and observing like or other people like cloud is the internet like a workspace, like not only for data but also for computation or like a storage. And yeah, these days, like at least in NASA's projects, if you are saying like I'm gonna do data analysis and I'm gonna do run like models or do some like model evaluation, you cannot win any proposal without mentioning like a cloud. First of all, I think the main reason is the NASA and like also NOAA and other like the U.S. government agencies like NSF, like they invest like so much money to cloud and try to retire their existing servers. So they would rather let the companies like the Amazon and Google to manage those like the servers. So they're gonna start to put all the new data into the cloud. So if you don't really leverage the advantage of those cloud systems, you're gonna be outdated. So that's really sad thing because I even see a lot of my colleagues, like those senior scientists, all complain that like now they say like the data there's no IP and like account where like they can ask their graduate students or postdoc like connect there and download the data and move it to our server and do some analysis. There's nothing like that. There are lots of like complaints, but if you are willing to learn a little bit about those like the advantages of like the cloud storage, for example, the CIMI6 model. We know that you can download like from through the ESG and it's almost similar to the conventional the FTP server. But they also put like the copy of the CIMI6 data on Amazon Cloud. And the biggest advantage is if you know how to use those cloud optimized like files, you don't have to download those data to your local server or to your own storage at all. So the data is sitting on cloud and you are running something on your server and only read like some parts of like the data and transfer the required like the data through the internet, and it doesn't save the data on your server until you say, oh, I want to save this data. So it only reads data from the cloud, and that data exists like on your RAM memory, and you can process without spending any of your local space, and only save like some subset or some processed data on your local server. That's the biggest advantage. But I think all like the U.S. government agencies haven't done a really good job of convincing the scientific community that you have to give up like your like local servers and like switch to cloud. So that's I'm having really hard time like trying to catching up because for example the Amazon cloud like probably announced like a new service and new like acronym, probably like 10 new service and 10 acronyms pretty much every day. So well, if you wanna talk about like this the Amazon cloud, and like also I can also share like my own experience as the Amazon Web Service. Yeah, so it's kind of irony because now if you say I'm not gonna use like a cloud, you get no money.
Yes. So we will have a last question from Facebook Live, Carlos Quantum Cannabis. He asked if in the case of ML, Do you use machine learning supervised or not supervised?
So you can use, both supervised and unsupervised.
Okay.
Yeah.
Both.
So yeah, for example, like the unsupervised like learning, you can just say that, oh, these are just a bunch of the persistent diagram or persistent images from data. Classify. I don't know like what they're gonna. Each class has any physical meaning, so you can do it. But if you have a already well classified and data set, like the atmospheric like a river case, you know which atmospheric river made a landfall and which one like did not. In that case, you can definitely use like the supervised like a model, and don't have to use the entire map and like thousands or like tens of thousands of pixels. What you need is like just the persistent diagram or persistent image of like a barcode, and let the machine like separate.
I have a question, a quick question.
Okay.
So since you're using different programs and different colleagues of yours, is there a particular program that you're using to run on this, or everybody does a little bit? And in which kind of platform do you do this? Like which program?
So everything, all the analysis, all the TD related part, like I only use one Python library.
Python?
Yeah.
Okay, that's good.
Yeah, so we had JPL host some summer school for graduate students, like every year. And last year, like at the NASA summer school, the climate summer school, I gave out some working code, like with the example of the temperature math, and students, could easily like run the code, and like now like they change the code and like try to look at the sea surface height, So it's easy, and so that's why if you just ask me, I can send you like the working code with some sample data. It's very easy. That's how like even the high school students performance.
Yes.
The two, I didn't use any like equation except the definition for versus distance, and there are a lot of complicated some mathematical background behind it. But as a user, you don't have to fully know all the basics and mathematics. But what you need to know is like the benefits of PD.
Yes, for a graduate student, they should look very carefully at the code so that it's not a black box.
Yeah.
Exactly.
Yeah. Cool. So thank you very much.